So to reiterate a little bit of what we talked about in the video with the orange, here I've got a graph representing the Earth, and on this graph, the red line is the equator, and the orange line is the prime meridian, and then we've got a point here. So if I go ahead and look at the Earth from the top, from the North Pole, and I change my longitude, we can see starting at the prime meridian, when I increase, I'm moving around the Earth. Then my latitude, again, 0 puts us at the equator. When I increase my angle, I move up. So that is going to be the convention that I am using when I work through the rest of this. So the way I have modeled the Earth, longitude is in the XY plane and moves us around clockwise, which is different than the usual direction we have angles in math. In math, usually we talk about angle theta moving counterclockwise. So that's an important distinction is I'm working with an angle that's moving me clockwise when it's positive. And the good news is that shouldn't matter too much because we're just going to be drawing pictures. And we can decide how we want to do things when we get to draw the pictures. And then our latitude is an angle that is going up from the equator. So with that in mind, we're going to look at a different visualization. So here I've got a visualization of the Earth, and then instead of being solid, I went ahead and did it more like the latitude and longitude lines, just so we can kind of see the way we're thinking about it. So how I think about this is, like we said, we need to figure out what the angle between the lines that get us to our points are. We need to be able to figure out that angle. And what better way to figure out an angle than to use a triangle? So if we think about the lines connecting to the center of the Earth and a straight line connecting the 2 points to each other, then we can see a triangle forms. If I want to know what this angle here is, one way I can answer that question is by using the law of cosines. And the law of cosines is going to be c squared equals a squared plus b squared minus c cosine, and we usually use a capital C, which is kind of hard to distinguish when I'm writing by hand. This is the angle across from side C. So thinking here, if I want this to be my angle, then I need this side to be my side C. It doesn't matter which of the other two sides are A or B, so I'll just go ahead and write them like that. So this is the way we want to approach figuring out what the angle is between sides A and B. So in order to do that, I need to know these distances. And the good news is there are some things that are pretty straightforward. Here, the distance from the center of the Earth to this point is going to be the radius of the Earth. So that's going to be the radius of the Earth. And so is this. So that simplifies things a little bit. So the distance here is going to be equal to, and I'm just going to use r for the radius of the Earth, r squared plus r squared minus 2 times r times r times cosine of that angle that we're interested in. So let's go ahead and do a little bit more simplification. We got c squared equals 2r squared minus 2r squared cosine of our angle. Again, we're trying to get this by itself. So we're going to have c squared minus 2r squared equals negative 2r squared times cosine of our angle. Going to divide both sides by negative 2r squared. And we're going to get c squared divided by negative 2r squared. So that's this part. And then over here, negative 2r squared divided by negative 2r squared, which is going to be plus 1, is equal to cosine of the angle between A and B. So now we've made a lot of progress just from using the law of cosines. The tricky thing is, how can we figure out this length of side C? So that's what we're going to be focusing on next, is how do we figure out this distance? Let's get to it. The first thing we need to do to figure out this distance is we need to figure out the coordinates of these points. If we figure out the coordinates of those 2 points, we can just use our distance formula to figure out the distance between them. So I'm going to go ahead and rewrite the formula that we found up at the top just so it's not lost, but we're going to save it for later. So we've got c squared over negative 2r squared plus 1 equals cosine of angle C. So looking at it here, sort of with a straight on perspective, I think helps me to think about the information that I'm trying to find. So what I want to start with is, how do I figure out the height of this point? In other words, how far in the z direction we've gone. So if I draw a little triangle just like this, there's some information that we know. Again, we know that this distance to the origin is the radius of the Earth. So that's nice. We also know that this angle here, our angle from the equator up to where we are, that one's going to be our latitude. So I've got an angle that I know, I've got a side that I know, and I've got a side that I want to know. So I want to know, okay, what trig function is going to relate this side and this side? Well, this side is opposite, and this one is going to be hypotenuse. So the trig function that relates opposite and hypotenuse is sine. So sine of my latitude is going to be equal to this z coordinate over the hypotenuse, which is the radius of the Earth. So our z coordinate is equal to radius of Earth times sine of my latitude. And that's going to be true for both points. It doesn't matter that I visualized it here on the Oregon point. It's going to be a different latitude for my South Carolina point. So our sine of that latitude will give me the z coordinate for my South Carolina point. So I'm going to do a little bit of thinking 2D and thinking 3D here when I talk about how we're going to find x and y. So first of all, we can imagine a triangle like this in our x and y plane, and that's what we want to figure out. What is x and what is y? The issue is, when I look at it at the top, it looks like this line here is the radius of the Earth, but actually, if we rotate, we are looking for our triangle is projected, so you can imagine there's that Z we just found. Our triangle, the hypotenuse, isn't the radius of the Earth. It's kind of like its shadow in this XY plane here. So I'll go back and talk about the angle we're working with, but we don't have any side lengths on this triangle like we did on the first one. So we are going to have to figure out, okay, what is this distance? So first, let's talk about the angle. So our is going to move us clockwise. And so it actually gives us this angle, not the angle in the triangle that we're working with, which isn't a big deal, but I'm gonna want to use this triangle. So how can I figure out what that angle is? Well, it's just this 180 degrees minus what we've gone so far. It's gonna be 180 minus our longitude. So that's the angle that we're working with, 180 minus our longitude. Now, I'm going to go back to looking at a triangle that we were seeing before. So we just found our Z using the radius of the Earth and sine of the latitude. Now I want to figure out, okay, what's this distance here? Sort of like the shadow of that radius in the XY plane. Well, I can still use my latitude as my angle, and I can use the radius of the Earth here to then figure out what this distance is. I'm going to call that distance h for hypotenuse because it's the hypotenuse of the triangle in the plane, the one that we're trying to get to, right? So this triangle here, that light blue line is the hypotenuse of the triangle in the XY plane. How can I figure that out? Well, sine related Z to the radius of the Earth. Cosine of our latitude is going to relate h to the radius of the Earth. Because h is adjacent to the latitude, and the radius of the Earth is the hypotenuse of this triangle there. So that value h is going to be equal to r times cosine of the latitude. So now we have an angle. We said this angle here is 180 minus the longitude. And we've got a side, we've got that h. So now we can figure out what our x and our y are going to be. So x is going to be equal to, x is adjacent to the angle. So if it's adjacent, I'm going to want to be using cosine because cosine relates adjacent to hypotenuse. So cosine of 180 minus the longitude is equal to x over h, which we found is our cosine latitude. So x is equal to cosine of 180 minus the longitude times h, which is our cosine. Okay, that's not showing up very well. We're going to go back to black. Which is our cosine of the latitude. So there would be our formula for x. Y is the opposite, so we're going to use sine instead of cosine. So sine of 180 minus the latitude equals y over h. And remember, h was, we found it earlier, r cosine. Whoops, I said latitude earlier. We're working with longitude now. Sorry about that. Okay, r cosine of the latitude was what we found for h. So y equals r cosine of the latitude times sine 180 minus the longitude. So with this information, we can now get the coordinates of each of our points. And we've got Desmos open, so we've got a calculator right here. When I originally made this visual, I did it in radians, which is just another measure of angle. So I'm going to change it to degrees, and it's going to make the pictures I had already go away. But we'll be able to calculate the numbers that we want. Okay, so looking here in degrees, we're going to get that the x-coordinate of Oregon is the cosine of 180 degrees minus the longitude of Oregon. So I put those up there, got O longe, and then times the radius of the Earth. The radius of the Earth that I used was in kilometers. Where did I put it? Which is 6,366 kilometers. Okay, so we've got times the radius of the Earth times cosine of Oregon's latitude with a lowercase l. So we've got an x-coordinate for Oregon. We're going to get a y-coordinate for Oregon. We said that y was equal to the radius of the Earth times cosine of Oregon's latitude times sine of 180 minus Oregon's longitude. Got a y coordinate there. And then our z coordinate for Oregon is equal to the radius of the Earth times sine of Oregon's latitude. Coordinates for Oregon. Now we're going to do the same thing for South Carolina. So the x-coordinate for South Carolina is going to be x, we said was cosine of 180 minus South Carolina's longitude times the radius of the Earth times cosine of South Carolina's latitude. Y-coordinates is going to be the radius of the Earth times cosine of South Carolina's latitude times sine of 180 minus South Carolina's longitude. And z for South Carolina should be the radius of the Earth times sine of South Carolina's latitude. Okay, so we've got some points. The distance formula is, so let's call it d for distance, is the square root of the square of the difference between each of these. So if I take, and it doesn't matter which one comes first, and take the difference between the x-coordinates of Oregon and South Carolina, square them. I'm going to add it to the difference between the y-coordinates for each of them. Square that. And the difference, oh, square that. So there we have the distance is equal to the square root, the difference between each coordinate squared. So now we've got a number here. What is that number? That was our length C that we were trying to find earlier. So if we remember our formula that we made a note of up here at the top, we say this is the C value we were looking for. So actually, I'm going to go ahead and change this from D to C. So cosine of some angle equals this number here. If I want to then find out, well, I'll go ahead and write that. So what we have now is cosine of our angle C is equal to this number. So if I want to figure out what the angle is, I'm going to do cosine inverse of this number. And what we get is about 36.1 degrees, which is the same angle that NASA got with their formula. So we have our 36.1 degrees. Now thinking back to with the orange, what that tells me is I've got some circle, I've got an angle of 36.1 degrees out of the full 360. So if I take, so the fraction of the Earth's circumference that I've traveled so far is 36.1 out of 360. And I'm going to multiply that by the Earth's circumference, which is about 40,000 kilometers. So if we plug that in over here, we get about 4,011 kilometers, just like NASA did. That is one way to think through where what the Earth looks like in 3D space in order to use the law of cosines and figure out that the distance between those 2 points on the surface of the Earth, on that rounded distance, is 4,011 kilometers.